We'll cover the Jordan lemma in this video. So, Jordan's lemma. Okay. So, before proving this, there is some thing that you have to define. You have to define first some tau of R. What is tau of R? Tau of R is a semicircular contour that is in the upper half of the complex plane. This is your real, this is your imaginary axis, and you are defining this as the tau of R. Okay, and the semicircle, this is a semicircular contour in the upper half plane, in the upper half plane of the complex plane, or you can say that this is the upper half of the complex plane. Okay, where this semicircle has some radius equals to your r, and if you take a point on this semicircle, this is nothing but a z prime, and you can write down the z prime is your r times e to the power I theta, of course. Okay, r times e to the power I theta, this is your theta. Okay, this is the first thing. Second, you are defining a function f of z in such a way that this z is defined on this upper half plane. This z is also defined on this upper half plane. That means for this z, for this z, the theta will be 0 to pi. You're defining the z in this upper half plane. That means the theta, that means your theta will be 0 to pi. Or you can say that 0 argument of z will be in between the 0 to pi. Okay. And another thing is that this mod value of f of z will tends to 0 when you are making the mod z tends to infinity. When you are making the, if you write down the z equals to any value on the upper half plane, z is equal to r e to the power I theta, smaller, this is smaller, and if you make the r tends to infinity, then your f of z mod value will tends to 0. This is the property of this function. And third, you are taking some alpha. What is alpha? Alpha is a real and your non-negative function, non-negative number, non-negative number. So these are the property of thing. Now you are defining some integral I of r. This is defined upon this contour tau of r and your f of z prime. Okay, the function f of z, we are saying that this is the function defined on a z on the upper half plane, and we are now choosing the z prime. That means we are choosing the z on this contour, that is z prime, and you are e to the power I alpha e to the power I alpha z prime and your dz prime. Okay, dz prime, this is the integral. And the Jordan lemma says that if you choose r tends to infinity, then is your ir equals to r tends to limit r tends to infinity, this integral tau of r f of z prime e to the power I alpha z prime dz prime. Okay, that will also tends to 0, or you can say this integral will be equals to 0. Okay, you have to prove this. Now you have to prove this. This is a proof. What is z prime? This is the contour, and you are choosing the z prime on this. This is r, this is minus r. Okay, this is a real axis, this is your imaginary axis, this is a theta. So z prime is nothing but a r e to the power I theta, or you can write down the z prime is equal to r cos theta plus iota sin theta. You can write down this, and you can write down the dz prime is equal to nothing but iota r e to the power I theta and your d theta. Okay, the dz prime is with that. So you can write down the ir as the tau of r. What is f of z prime then? F of z prime equal to r e to the power I theta e to the power I alpha z prime is equal to your r cos theta plus iota sin theta. Now what is a dz prime? Dz prime is equal to I r e to the power I theta d theta. Okay. So what is your IR then? IR is equal to I R. You can write this outside of this. This is R e to the power I theta and e to the power I alpha R cos theta plus theta and it will minus alpha times R. There will be also R because R is multiplied with both sides. Okay, alpha R sin theta and here d theta. Okay, now look into this. We have said that f of z tends to 0 and this is not the f of z, this is tends to 0. There is a term uniformly. So f of z or mod value of f of z, whatever you say. So mod value of f of z, or you can say f of z. So f of z tends to 0 uniformly when you are making r tends to infinity. Okay, when you are making r tends to infinity. To say this mathematically, we say that uh, to express it mathematically, we say that f of uh, mod value of f of z is less than of epsilon of r. We are choosing some epsilon r. Epsilon r is a epsilon r is what? Epsilon is a positive number. Epsilon r is a positive number. Okay, positive number. And the thing is that when you are choosing the r tends to infinity, this your epsilon r will also tends to 0. That means when making the r tends to infinity, this mod value of f of z will be less than of some infinite small value, because epsilon naught also tends to 0. And if there is an infinite small positive value, and an f of z, mod value of the f of z will be less than of that infinite small value. That is the way to say that f of z will uniformly tends to 0. When you are there is right now the uniformly tends to 0, this is the mathematical expression you have to use. So if you put this, then your IR and another thing, the maximum value of this is 1, right? You can choose as this as a phi, so e to the power I phi, and e to the power I phi as a maximum value is 1. Okay, or instead of that, if you okay, and this maximum value equals to 1, you can say that. Okay, so you can write down this IR mod value. IR mod value is less than of R times tau of R epsilon of R times e to the power minus alpha R sin theta d theta. Why? Because this value is less than this. Okay, this value is less than this, but you can instead of saying that this is the mod value or get a maximum value, you can say that if you take the mod value here, okay, you're also getting the mod value here. That means you're getting the mod value of f of z here. When you're getting the mod value here, you're also getting the mod value of this. Okay, and the other part is this. What is the mod value of this? Is equal to 1, and the mod value of f of z is less than epsilon of r, right? So you can, instead of putting the equal sign, you can all easily put the less than sign. Okay, because the mod value of f of z is less than that, and you are putting this in the integration. That means the integration will be, this integration will be less than that. Okay, so it will equal minus, you got this right. Okay, now now there is another trick. There is another trick that sine theta. Now before that, your I of r is less than r epsilon of r. You can put this out, and as this integration is only upon the theta, you can put the 0 to pi, because the integration in the theta domain is 0 to pi I alpha sine theta and your d theta. Okay, then is there, you can write down this IR is less than r is less than r times epsilon of r, and 2 times 0 to pi by 2 e to the power minus I r sine theta d theta. Why? Because sine theta is symmetric about the pi by 2. So you can write down the 2 times 0 to pi by 2. Okay. And now the thing, sine theta is always greater than, sine theta is always greater than 2 theta by pi when you're taking the domain theta in between the 0 to pi by 2. Because if you plot the y is equal to sine theta, and if you plot the y is equal to 2 theta by pi, you can easily see. Okay. This is your y is equal to sine theta. This is your pi by 2. And this value is 1. And if you plot this y is equal to 2 theta by pi, that is slope is 2 by pi, then you get something, some line, this straight line. And you easily see that in between 0 to pi, sine theta curve is above this, then sine theta value is greater than this 2 pi by theta. So here, and another trick, you can take this is e minus x. So that what is the value? That means sine theta has a minimum value of this. So you can always know that e to the power x is less than e to the power minus x minimum, because this is negative. So if you take the minimum value, that will be more, that will be greater than this. So you can write down this integral is less than e to the power minus alpha 0 to pi by 2 times r times sine theta minimum, that is a 2 theta by pi into d theta. So you can write down this IR is less than R times epsilon of R times 2 times 0 to pi by 2 e to the power minus alpha R 2 theta by pi times d theta. And if you do the integration, you will get some I epsilon of R into 2 times pi by your alpha times R times 2 into, if you e to the power minus alpha R 2 theta by pi with a negative sign 0 to pi by 2. And if you do this, you'll get some alpha, this r will cancel out, 2 cancel out. Okay, you'll get epsilon of r times pi by alpha, and here you'll get some e to the power minus alpha, e to the power minus alpha times r. This is your mod value of IR. Okay, now if you put the r tends to infinity, these values go to the 0, and this whole term will become 1. This is just a positive and a non-negative and real value. This is constant, and you already know that we have chosen epsilon r in such a way that that value is positive but tends to 0 when r tends to infinity. Okay, that means epsilon r will be some less than of, because this is positive, this is positive, this is also positive but tends to 0. That means this is less than of some positive infinitesimally small value. So infinitesimally small positive value থেকেও কম, that is less than of that value, that means I of r mod value is nothing but 0. Okay, so there is an infinitesimally small positive value, and I of r is less than of that, that means I of r is nothing but a 0. So you can say that what you are trying to prove, this, the limit r tends to 0, is value is 0, because mod value of r is 0. So if the integral value, after doing the integral, we are getting the complex value. If the mod value is 0, then it's the complex times the mod value. Okay, so I of r complex times it equals something, whatever the value. If you take the complex, I mean if ir is complex, and this of ir equals to a mod value times something, it equals some phase part. If this part is 0, so ir will be 0. So this is the proof of Jordan lemma. And if you take alpha equals to negative, then you have to choose some contour in the lower half of this complex span, you will get the same value.